Hello everyone. Welcome to this interesting video session on Kepler second law. So today we are going to derive about Kepler second law. So the second law is actually called as the law of equal areas. Okay, law of equal areas. Now here we'll try to derive the expression for what is law of equal areas and how it plays a very important role in planetary mechanics. And in fact, in the last conceptual video, we have already seen what is law of conservation of angular momentum, which clearly states that your h is going to be a constant. So uh, these things we'll try to implement here so that we'll get a good expression, some mathematical meaning to this law. So we'll try to derive Kepler's second law without wasting much of our time. So let's consider an orbital path. Now I'll try an orbit with having an elliptical path. Now while drawing you can use your instruments and you can draw accordingly. So here we'll draw it in a simple fashion. So this is your ellipse. Now let's say this is your ellipse. Now I'll mark the points. Now from this point to this point you have, let's say you have 2a, that is the major axis distance. Okay, so here it will be, let's say this is the center, let's say this is C here, or you can take O. Okay, you can take it as O. Now this is your semi-minor axis, so which is less relevant. Let's say we are not considering anything. So geometrical, this should be symmetrical. Okay, so geometry wise, while drawing, this should be symmetrical. So this should be B, this should be B, this should be A, this should be A, because it's symmetry about 50-50 half. We have done it with the help of the axis division. So this should be A, this should be A. So total makes the 2A. Okay. So now this is the foci. Now let's mark the foci here. This is having two foci. Now what we draw is like we have a big planet, big celestial object, that is your sun, which is ultimate source of energy. So sun is here. Now your planet starts revolving here and started to approach over here. Okay. Now we draw a line from this point. We have a common point here. So let's draw a line from here to here. This should be straight actually, but by freehand it got a bit of curve. So it should be a freehand sketch. So should be straight here. So freehand make some curve here. So it's okay. While practicing, you can do it accordingly. And now we consider this small curve had to be a somewhat to be a straight. Now we have a small angle 90-degree here. And now we have a small angle we'll consider, that is called delta theta. Okay, so since it is been acting on the aphelion, so we have an aphelion radius Ra. Okay, and this delta theta which is subtended can be written as delta theta A. Okay, so this is aphelion. Similarly, some area is being swept over here as well. So from here it has reached to the smaller distance. So I'll draw again a common point, and here you get the distance from this point to this point, that is called the perihelion, Rp. Okay, we have Rp and Ra. So distance from the sun to this point is the aphelion, maximum distance, and distance from here, this is called the perihelion. Okay, now I can draw this triangle in a separate. So we have a common point. Let's say we have a big common point called A. Okay, now this is my ears. From with reference to here, I am trying to draw here so that it will be clear for you. So this is the total distance is Ra. So I name here, this is 90 degrees. So I name a small distance which is being exhibited called dx or something. Okay, now we have the smaller angle that is called a delta theta A. Okay, now this is sweeping some. If you closely observe, we can see some small area which is being imparted here from this point to this point. So let me share that point. So this is my area, just like a cake piece, you can tell. Okay, this is called the area. which is represented like this here. So let this area be A1. So this is the exhibited area A1. Let's say the small area, in fact, so delta A1, I can write delta A1. So similarly, if I draw the same stuff over here, so this is A, so I draw the same stuff over here. Okay, so I have this, so this is bit small actually, so I'll just take small actually. So here we have delta. Okay, now you don't have to consider this extra line, so it's okay. So we are only deal with only this curve. Okay, now we have small angle, let's say delta theta p. Okay, here also we have delta theta p, this angle. Okay, so now this is actually the total perihelion distance, which is being given by rp. Okay, so from here, from a point to up to this much is Ra. So this is pretty clear. I think hope this is understood. Okay, now we have two triangles, so I'll name these triangles. Okay, A, B, C we can take. So here A, B dash, C dash. Okay, now you should remember one thing. At the periapsis we have a smaller triangle like this. Okay, now let's say we have delta theta p, and this total is going to be your area. So this is actually an area of a right triangle. Okay, so this is B dash, this is C dash, this is RP distance, and this is going to be a common point. Now you can tell me what is the area of this triangle. So area is equal to area of the triangle A, B dash, C dash is going to be the basic formula which you have to learn, half into base into height, which you have already learned in your primary schools, especially in the metric level. Okay, so half into base into height. So here we have so here we have taken dx, let's say dx, so we cannot take the dx again, but we'll take something called dx1 or something. Okay, which will be pretty more clear for you. So we'll take dx1 or something here for regarding the perihelion part. So we have dx1. Okay, fine. So here in this triangle we have dx1, so we are taking the perihelion side. Okay, dx1. So dx1 is going to be, if you have tan of a small angle delta theta p, then you can tell me that your tan delta theta p is actually equal to opposite side dx1 divided by r of p. Okay, now if tan delta theta p, again we make an approximation as delta theta p is bit small, so we go with delta theta p is going to be equal to dx1 divided by rp. So dx1 is equal to delta theta p into rp. I hope this is clear. So in this triangle we can write your base is equal to your r times of r suffix. Okay, it should not be times, it should be suffix. So base is actually rp, this is the perihelion distance or the perihelion radius. Now your height is nothing but dx1, so it is nothing but here delta theta p into rp. Okay, therefore your delta a1, or sorry, here it is delta a2, so delta a2, because here we have taken delta a1, so obviously here we are going to take the area of this triangle. Okay, now that should be delta a2, that is the area of this triangle. Okay, so delta a2 is going to be half into, this is basic elementary math, so half into what is base rp into delta theta p into rp. So this you are going to get delta e2 is equal to half into r square p. So I'll make it move this side, so which will be visible for you. So r square p into delta theta p. As this is happening, so this sweeping of area is happening at some interval of time. Let's say for periapsis or perihelion, it is happening at delta t2. So if I divide by delta t2, at time interval, okay, at small time interval, delta t2, okay, at small interval of time delta t2. Now let's say you have delta a by delta t2, okay, so which is going to be half into r square p into delta. You can write here delta theta p divided by delta t2. This is something like omega, okay. This is called the angular frequency, which is also called omega, which is equal to delta theta times delta t. So this should be omega p then, okay, at the perihelion. Omega r square into p. So that is called as the delta A2 divided by delta T2. Hope this is clear for perihelion. Okay, this is for perihelion, the smaller triangle, which you can see from the figure. This is a smaller triangle. So we have considered the area for this particular triangle. Okay. Now my interest will be, so this will be happening at at perihelion. So at perihelion we have delta A2 divided by delta T2, which is equal to half into r square p into omega p. So I don't want to go with the other further stuff. We have r in half into r square p into omega p. Okay. Now if you consider the similar way of solving it, again you have a triangle. Okay, at aphelion. So we can write it very fast. At aphelion you have delta A2. So which is given by again half into base into height. Okay, I don't want to write, still I am writing this because it will be clear for you. So this will be half into, what is the base here? So base is, here it was rp, so here it will be ra. What is the height? You can tell from here itself, it is delta theta a, okay, into r of a. Okay, as now this is happening at some time interval, this is sweeping this area at some time interval delta t2. This is going to be, so here it is, you have to be very clear with the uh, denotation. Okay, this should be 1 actually, because we are considered the aphelion. Okay, so delta a1 divided by delta t, this is where you make some mistakes. So delta a1 is equal to half into base into height. So delta a1 is equal to half into, so ra into delta theta a into ra. So delta a1 by t1 is equal to half into delta theta a into r square a. So again we have a small time interval t1 here. So delta a by t1, it is nothing like your half times omega into r square a. So this is happening at the aphelion. Okay, so that means equal to delta a1 divided by delta t1. Hope this is clear. Okay, now if you see the conservation of angular momentum, we have h is equal to is a constant term, which I have already proved in a previous video. So that means your m into omega r square at any position is going to be a constant. Okay, so that means your m omega square at apoapsis is equal to m omega r square in the periapsis or the perihelion. Okay, if mass is going to be same, then probably you can cut it off. So you get with omega a into r square a, this should be equal to omega into r square p. Now you divide by 2. Okay, ultimately you end up with these two terms. So this is nothing but your delta a1 by t1, delta t1. So this is delta t2 by delta a2 by t2. Okay, because this is the equations which we get in the finally. Okay, so here we have this equation delta a2, this is something just like this one. Okay, and delta a1 by t1 is half into this one. So if you see here, this is nothing but again delta a1 divided by delta t1, this is equal to delta a2 divided by delta t2. Okay, so this is for the first, okay, and this is for the second. So we have equated it. Now we'll write it neatly here. So ultimately we are going to get delta a1 divided by delta t1, which is equal to delta a2 divided by delta t2. If this is keeps going, then we are going to get delta a1 divided by delta tn. Okay, So why it is called the law of equal areas? Because if the area is going to be same for equal time intervals, okay, let delta t1 is equal to delta t2 is equal to some time delta t, okay, then your equation is going to happen delta t is equal to delta e2 divided by delta t. So your t gets cancelled off, you end up with delta a1 is equal to delta e2. That means your planet sweeps equal areas in equal interval of time. If delta t1 is equal to delta t2, that means the equal interval of time. So that means delta a1 is going to be equal to be delta a1 is equal to delta a2. That means a planet sweeps equal areas in equal time interval. That is what we are trying to convey. Okay, I hope this video is clear, and make sure that you visit my further videos in the coming sessions, and all the concepts has been explained previously. You can have a look and make sure you will work out those, and we'll see in the next video. Hope you like this video, and we'll catch up in the next video then probably. And if at all having any doubts, please let me know in the comment box so that we can discuss accordingly. Okay, thank you so much.